Thanks for joining us. This is the Lambda Expressions talk in the Back to Basics track. I'm Barbara, and this is Ansel. We have lots of information to cover today. Since Lambda Expressions have been updated 3 times since C++11, there's a lot of new information. If you're watching this live, please feel free to post questions in the Q&A. We're going to try to answer them in real time. If we miss a few questions, we'll be available after the talk and in the hallway track later on. So we're going to start with an introduction about who we are. Ansel and I are the co-founders of the CopperSpice project. And CopperSpice is a cross-platform set of GUI libraries. All of our work is open source and everything is available on GitHub. But CopperSpice is more than a set of libraries. It's also a team. Our developers, our contributors, our testers, people that help with documentation. We're located all over the world. And if you're looking for an open source project and you don't feel like starting one yourself, because it is a lot of work, please consider joining our team. Contact us during the conference or send us an email. And please take some time to download CopperSpice and take a look at it. There's one product that we have that we'd like to point out, and that's Doxypress. Doxypress is an application which is used for documenting your source code. And it takes your source code and your comments and merges everything together. If you happen to be using C++20 and you need to document concepts or the new requires clauses, it turns out we've already accommodated this and we've added it to Doxypress. We do believe we're one of the few documenting programs that actually understands C++20.
So whenever we do a presentation, we always like to start with a bit of background about the topic. And we wanted to look at the question, where did the term lambda originate from? Well, the word lambda comes to us from the lambda calculus, which is a branch of mathematics that focused on trying to ask the question, which problems could in theory be solved by a computer? It predicted that a lot of problems can be solved by a computer, which is a bit surprising because back then computers were very limited. Keep in mind, in the 1930s, personal computers were decades away. So functions in the lambda calculus have no names. And lambda calculus used the Greek letter lambda to define a function.
On the wrong slide.
So the word lambda became associated with the idea of a function with no name. Now, a lot of developers focus on that and get the idea that a lambda refers to something nameless, which it does. But that's one of the least important pieces of a lambda expression. So why do we use the word expression in this term, lambda expression? Well, what is an expression? Well, 5 plus 2 is an expression, and it returns a value. Int x is a declaration, not an expression, so it doesn't return a value. So expressions, one of their parameters is that they return values. The fundamental definition of a lambda expression is that it is an expression that returns a function object. Well, now we have a new term, so we need to define a few more things to understand what a function object is.
But our journey really starts with a review of function pointers, because we need this background first. A function pointer is a data type whose value points to a particular function. What's important is that a function pointer does not point to data, which is really what a typical pointer is for. So unlike a normal pointer, a function pointer is not dereferenced. So here's a quick example using a function pointer. Just like a normal pointer, you declare a function pointer with a star. But when we call it, there is no star used for the dereference. Our pointer, it's named myProcess. Our function pointer, it can point to any function which has a single parameter of type int and a return type of void. So in our example, myProcess is initialized to point to std exit. So on the last line in this example, when my process is called, the program will exit with the error code of 42.
Now notice if you look at this last line in isolation without any of the other code, it looks as if my process is a function. And that turns out to be a very important attribute of function pointers. Now we also need to define the terms overloaded operators and the function call operator. Well, an overloaded operator is simply a method whose name is the word operator followed by some symbol. And a lot of us have written these in our code or used them on a regular basis. We have assignment operators, comparison operators, increment operators, things like that. The function call operator is a special case of an overloaded operator, where the symbol that you're overloading is a pair of parentheses, the open close parens. And you'll note toward the bottom, we're showing some examples. There's two sets of parentheses. The first pair is always empty and it's part of the name. And then you have the function parameters.
So any class which declares a function call operator, this is called a function object data type, but it is still a class. This is very similar to the way we refer to an std vector. We call it a container, even though it's a class. An instance of a function object data type is called a function object. So we're going through all these definitions so we can understand Lambda expressions. We're going to be tying it all together, and hopefully that will make sense. So we've been talking about a function object data type and a function object. What is really important to remember is when you call a function object, you are really invoking the function call operator. And remember that function call operator is what we showed in the last slide, the operator open close. So here's a base example. We're declaring a function object data type. Ginger is a class. It defines a function call operator. You can note that by the operator open close and then the second set of parentheses with the data type. On the following line, we construct a Ginger object, and this is named widget. There are two ways to call our method. On line A, we invoke the method directly. It might look a little odd because we do need the operator open close and then the second set of parentheses to pass the parameter. Line B is a bit different. We're taking the function object widget, and this is called as if it were a function. What this is actually doing is calling our function call operator, even though we did not spell out the word operator.
And notice that just like in the function pointer case, if you look at the very last line in isolation, it looks like widget is a function. This means that the syntax is the same, regardless of whether you're calling a function pointer, or a function object.
We want to throw something in here at this point, and this is actually important to us. C++ programmers, they like to use the word functor. The standard actually doesn't mention this term, so it doesn't have a definition based on the standard. If you look around the internet, you can find lots of definitions for the word functor, but usually they pertain to math or functional programming.
We've found that typically when C++ developers use the term functor, what they really meant was function object. And why does this matter? Well, if we want to be able to communicate effectively about the code we're writing, we really need to be using the right terminology and developing good habits. We feel like you should use the standard terminology whenever possible.
So here's a quick review of what we've talked about. We have a lot of terms here: functor, function pointer, function object data type, and function object. It is really easy to confuse all these terms. They sound very similar. The two terms that we want to expand on and relate to Lambda expressions is a function object data type and a function object. These are the main terms of interest to us. Now, std function, this is also really important, and it was added in C++ 11. And the main reason why they added it was they wanted a class which could be used to store a function object. So this actually provides a mechanism for passing a Lambda expression to another function.
Now, there's a lot of syntax in a Lambda expression, and the order of all the different pieces really matters. There are three main clauses which appear in the square brackets, parentheses, and curly braces in that order. The return type, which we're showing in purple here, is optional and is usually not specified. And we're going to talk in detail about all of these elements as we go on. But for the moment, we want to call out the fact that since a Lambda expression produces a value, the result can be stored in a variable. This variable should almost always be declared with auto because the data type of a Lambda expression is compiler dependent.
So these are the key sections that pertain to a Lambda expression. We have the capture clause, and it specifies which variables will be available inside the body of the Lambda expression. It's not necessary to capture anything. However, the square brackets are required, so you have to have them. The parameter list is very similar to the parameter list for a normal function. The parentheses for the parameter list, you can leave them off, but then it makes everything look a little odd. So we strongly suggest keep the parentheses there for the parameter list, even if you're not using a parameter list. The return type, it's only required if the compiler cannot deduce the return type. And we will talk about that a bit more. The body of the Lambda expression, this is enclosed in the curly braces and has the same meaning as any other function body. What we do want to mention is that the body of the Lambda expression, this is what becomes the body of the function call operator. So we want to keep bringing that up. So we're relating a Lambda expression to a function call operator. So here's an example, and it shows a simple Lambda expression. We want to capture X and print the value. The question is, what value is printed? If you're watching this talk live and you feel like typing the answer in the Q&A, we'll take a moment to read those as we continue to go over this example. So, looking at the code for main, we have int x equals 42. X is in the capture. And it must be declared before the Lambda expression. But if you notice, X is reassigned to 7 before myLam is invoked. And I see some people posting and voting up. That's a good thing. We're seeing some answers appear. Notice, this X is captured by value.
And this capture means that the value is copied when the Lambda expression is evaluated during the initialization of myLam.
So yes, as people are posting, 42 is the answer because the capture actually happened during that declaration. So the fact that we're reassigning X to 7, that doesn't have any bearing on what it actually prints when the Lambda expression is evaluated and the result is printed. But let's change things up a bit. So what happens if we capture by reference?
So what value will we be printing in this case? Well, the capture by reference still occurs when the Lambda expression is evaluated. So we haven't changed when the capture happens. However, changing the value to 7 will be visible to the body of the Lambda expression because what got captured is a reference to X, not the value of X. Now, there's something to keep in mind here. Since the Lambda expression now uses a reference, if X had gone out of scope before we invoked myLam, then you would have a reference to an object whose lifetime has ended, and you'll have undefined behavior.
We want to be a bit picky right now, which is sort of what we do as programmers. So everything to the right of the equal sign is what we call the Lambda expression. The expression is evaluated, and then the variable myLam is initiated and initialized. But we're using a variable called myLam. It's easy to say, it's easy to hear and to pronounce. But somebody suggested maybe we should be calling this myLambda expression as a variable name. Well, that is an interesting term, but keep in mind, once we evaluate the Lambda expression, it's not actually a Lambda expression. At that point, it's a closure. So maybe we should have called the variable myClosure. That is also an option. But the truth is, myClosure doesn't really say anything about the code.
Now, we just mentioned the term closure. And the question is, what is that? Well, in C++, a closure is a term the standard uses for any function object which is returned from evaluating a Lambda expression. That's all it is. It's just a category of function objects that came from Lambda expressions.
So the key point is, yes, we're using a silly variable name. We encourage you in your production code, pick variable names that actually make sense. And that isn't my Lambda expression or myClosure. But we're just going to use myLam in this talk as a way to pronounce it. And we've explained now why we're using that.
So we want to go a bit deeper in detail about the different clauses in a Lambda expression. And first, we're going to cover the capture clause. When you capture a variable by value, it gets copied into the function object as a const value. The only things you can capture are variables in your local scope and various forms of this. You can have any number of variables in the capture clause. And since the variable is being captured by value, it doesn't matter if the original variable goes out of scope before you invoke the Lambda expression closure. If you want to be able to modify the captured value in the body of the Lambda expression, you need to mark the entire Lambda expression mutable. This will make the capture by value rather than by const value. The word mutable needs to appear just before the body of the Lambda expression.
So here's a capture, and you can see the ampersand X. This is an L value reference. It's not valid to capture by R value reference. So all we have is L value. We'll talk a little bit later on other ways of handling R value references. But keep in mind, when you have a capture clause, you can capture by value and by L value reference, and you can mix this up within the capture. So when you capture by L value reference, make sure the data remains alive for the lifetime of the closure. We have a question that just popped up. What about global variables?
Well, that's a fascinating question. And it turns out the answer is you can't capture global variables, but you don't need to because they're visible directly from the body of the Lambda expression. So there's nothing to capture and there's no reason to.
So taking a look at this code again, there's a bit of a subtleness we want to point out. The variable X in the capture, we're saying we're capturing by L value reference, but that doesn't actually indicate or have any bearing on how X was declared in the outer and local scope. So you can't draw any conclusions. So X may have been declared as a value in the outer scope, but we're saying in the Lambda expression, it is an L value reference. That is how we're going to capture the data. So the capture clause declares what the Lambda expression sees. And again, you need to ensure the Lambda expression can refer to the data So you do not move or destroy X if that closure, while the closure is still alive. So there's a big difference. If you're capturing by value, then it can go out of scope in the outer scope. But if it's by reference, it has to stay in scope.
So in C++11, all we had was capture by value or capture by reference, as we've just discussed. In C++14, the capture clause was extended, and they added a feature called generalized capture. So what is this?
So generalized capture has various forms. And all of these, the syntax will look like it's doing an assignment. In our first example, you can see that we're doing the capture and we're saying var a equals 10. So we're assigning the value 10 to var a. In example 2, we are capturing the value of x and assigning it to var b. And as we've stated, since x is in the local scope, when we capture that and assign it to var b, x can actually go out of scope because we now have captured the value and saved it in var b.
The last example we're showing here has a move capture into var d. This allows using a generalized capture to move a value from the local scope into the closure. Now remember that captures happen when the Lambda expression is evaluated, even if the closure isn't invoked until much later. So this move operation is going to occur where the Lambda expression is defined. You can't use the move captured data after the Lambda expression is declared because the value in Z will be gone.
So the fact that we're talking about there's problems if you try to access a variable after it's been move captured into the Lambda expression, this is actually nothing specific to a Lambda expression. This is just the understanding of how a move capture works. The problem is, if you're reading a particular method and you're looking at code and you see that there's a move capture, you tend to glance over the code and see, oh, wait a second, we're using this later on and we've move captured. The problem is sometimes when the move capture is part of a Lambda expression that has been declared several lines above in the method, that you don't see that the Lambda expression is called later on. So that's why we're trying to point out, you need to be careful if there's a move capture that everything stays in scope for that variable.
So just remember, if you're writing code and you're using C++14 generalized capture, the capture clause itself can have side effects.
So what happens about a Lambda expression inside a class? Well, you don't have access to the data members and the methods. So how do we capture the current object? We need a way to capture this.
In C++11, the only supported way to do this was to capture the this pointer. This is capturing this by value, but since this is a pointer, you will have a pointer to the original object. That means modifying this arrow some data will change the original value. In C++14, you can use a generalized capture to copy the current object into some other variable. At this point, inside the body of the Lambda expression, if you modify self.someData, you'll be changing the copy. In C++17, the capture clause was enhanced to allow capturing star this without changing the name of the variable. The only issue with this is the fact that the C++17 syntax, which captures a copy of the current object, is only one character different than the C++11 syntax, which captures a pointer to the current object. So you have to be very careful in reading modern code to ensure that you know the semantics of what's being done.
We have a question. When a capture initialized by reference, what is visible in the Lambda?
var
X or var Y?
I think that may be a question on the previous slide.
Yes.
If you mean var C or Y, the answer would be, based on this code, that var C is what's visible inside the Lambda because that's the name of the capture. Y would have to be a name in the outer scope that evaluates to something which can be captured.
If there's more to that question, feel free to post. Otherwise, we'll move on. And we'll go to the next slide. So here are a few more ways to capture. And we're going to say that this maybe should be used with a little bit of care. You can specify a default capture where any variable which is used in the body of the Lambda expression will automatically be captured from your local scope.
Now, the first example here says I would like the default for any variable I refer to capture by value. The second example says I would like any variable I name to be captured by L-value reference. Both of these examples refer to X and m_data. And in order to compile, these both need to be either in the local scope or class members. Assuming that mData is a class member, this will be default captured because we need access to it in order to access that variable. This means changing mData will alter the original data member because it doesn't matter if you capture a pointer by value or by reference, you're still referring to the original object. Starting with C++20, the default capture of this by value is deprecated because it's a bit surprising that you asked for everything to be captured by value, but this was really a pointer. So in C++20, the first example will generate a warning when it's compiled.
We have another question. Does evaluating the Lambda expression happen when it's defined or when it's first run?
That's a great question.
That's a great question.
Yeah, it is a great question. And it really points to the fact that Lambda expressions sort of get run in two parts. When we say evaluating a Lambda expression, we're talking about the process that occurs when it's defined. Then later on, when you call the closure object, we call that invoking the Lambda expression. And it's important to keep in mind what happens at each of those phases. The evaluation of the Lambda expression does all the captures. The invocation of the Lambda expression runs the body. Great question, thank you.
Excellent. Can you call the closure mylam from the Lambda expression? I'm thinking about...
I think that question is asking inside the Lambda expression, do you have access to the closure that you're in? I believe the answer is no.
Yeah, we say no.
But we'd have to check on that.
We'd have to check on both. Okay. So we have one more definition for the capture clause. The C++ standard says any object created by a Lambda expression is a closure. But if there's nothing captured, the standard actually defines this as what's called a special kind of closure. And this has a purpose.
These special closures can be very useful when you're calling legacy code or some C API which expects a function pointer, because these special closures can be implicitly converted to function pointers. That means you can call this API and pass a Lambda expression as long as there is no capture, and it behaves like you passed a function pointer.
So now let's go on and talk about the parameter list in a Lambda expression. Yes, it can be empty, it's optional, and we said you can leave off the parentheses, but it really does improve readability. So the parameter list, you already really know this. It's similar to a normal function parameter list. In 11, default parameters are not allowed. This was actually an oversight in Lambda expressions. They didn't intend this to happen, but they just kind of forgot. What's a little interesting is people say sometimes it was fixed later on. This oversight was actually fixed retroactively in C++ 11. The reason why we mention this is if you happen to be using an older C++ 11 compiler, this may not have been resolved. So if you're seeing a problem with default parameters and you're using 11, you may just need to update your compiler.
C++ 14 added the ability to declare a Lambda expression parameter using the data type auto. And when you put auto in for at least one parameter, that Lambda expression is called a generic Lambda. And we're going to cover generic Lambdas in more specific detail a bit later.
The return type, as we've said, is optional as long as the compiler can deduce it. In 11, the compiler could deduce it if there was, and you could only have one return type. So if it could be deduced, fine. In 14, you can have multiple return statements now, but these return statements have to return the same data type. Now, the example we're going to show here, it is a bit silly. And the purpose of this is to show a use case of when you have to specify the return type.
So in this example, we have two return statements, and they return different types. The first one returns an int. The second returns a double. These are both convertible to a common type. You could convert them both to double, but the compiler won't do that. It will simply fail with an ambiguous return type error. Since we're explicitly specifying that we want this Lambda expression to have the return type double, our example will compile fine, and the 3 will simply be converted to 3.0 in the return.
In C++ 20, Lambda expressions became a little bit more involved. There's more sections added. And we want to spend a little bit of time just going over what these new sections are. But all of them are optional. So if you look at this example on the screen, this is what it's going to start to look like with a Lambda expression. Notice the first one and the last one are highlighted in yellow. These are the two that are required. But we're going to start by talking about the fact that they've added the ability to include template parameters.
This was added for a number of reasons, but one of the most important is that in order to support C++ 20 concepts, you needed a way to specify a template parameter list on a Lambda expression.
So we already did talk about the mutable specifier. And in 17, they added the ability to mark a Lambda expression const expr. This is actually a bit confusing because C++ 17 is required to check and see if it can deduce something as const expr. So if you're using 17, you really don't need to mark your Lambda expression as const expr. That's going to happen automatically.
So the question is, why would you mark a Lambda expression as const expr? And the only reason to do this is if you have a Lambda expression that you need to be const expr, then marking it const expr will cause a compile error if the compiler cannot deduce its const exprness. In C++ 20, you also gain the ability to mark a Lambda expression as const eval. And this acts very similar to the way const expr does in terms of the Lambda expression. But as far as what const eval means, we'll leave that one for another talk.
We have another question that just popped up that's on slide 25, talking about, I think this was the special kind, and does it have a specific name?
Regrettably, the specific name that it uses in the standard is a special type of closure. So that is the technical term from the standard of what it is called.
And somebody's asking if const expr can be used inside a Lambda expression.
That's a fascinating question. And the answer is yes, if that Lambda expression is generic, which follows the exact same rules as the rest of the language, because if const expr needs to appear inside the body of something which is templated. And yet, so you can use if const expr within the body of a Lambda expression.
Yes. Okay. So the next clause we have is the exception specifier. This actually hasn't changed since 11, but we thought it'd be good to bring it up. Marking a Lambda expression as no except, and this is going back to the fact of why we talked about the function call operator. So remember, what you're actually writing is basically a function call operator in the body of your Lambda expression. So if you're marking it as no except in the specifier, when the closure is invoked, it cannot throw.
Now we come to the function attributes, and this one's a bit tricky. Not many people know this, but there are actually two different groups of function attributes in C++, based on where they can appear in the declaration. For a normal function, the attributes that we typically use, like deprecated or no discard, they appear in an attribute block before the return type. And these are called function attributes. Those are not currently supported on a Lambda expression. There is a proposal pending to add this, but it hasn't made it into the standard yet, and it's not clear if or when it's going to be added. There's a second set of attributes which appear at the end of a declaration. These are called function type attributes, and these modify the signature. These are all compiler and platform specific attributes, usually things that change the platform ABI calling convention, like GNU::cdecl. These attributes can be placed before the return type of a Lambda expression. But don't try marking a Lambda expression no discard, it won't work yet.
So the last section we have is the requires clause, which is located just before the body. And this is used to add a constraint on the Lambda expression. And as you can see in our example, we have a constraint on T, and this is checked at compile time. We want to make sure that T is copyable. And this example, that's exactly what a requires clause will look like in 20. And you can put it in your Lambda expression. And to use this, it does require that the Lambda expression be generic. We were just talking about that with the question. And again, what makes it generic? There has to be a template, a T, in the template parameter list, or at least one parameter in the parameter list has to be marked auto. Keep in mind, in 20, you will be able to mix this. So in a parameter list, you can have one thing auto, you can have a template parameter. It's not just one thing. You're allowed to mix these all up. Will these slides be available? Yes, we will be making the slides available afterwards. Thank you. So this brings up a really interesting point to us. Why are Lambda expressions so darn important? You can write the equivalent code. You can write the function object data type. You can write the boilerplate. So why did they go to all of this work? It's more effective to write the body of the function object and let the compiler do the rest.
One of the really nice things about Lambda expressions is as we move more toward a functional style of programming in C++, as many programmers are, calling functions like stdvisit just reads better when you use a Lambda expression for the function object, because all the code that's needed to understand the expression is present in one place. One of the things that's really amazing about the way Lambda expressions were implemented is that all of the existing standard library functions, like algorithms, still work perfectly with Lambda expressions and didn't need to be changed. This is a testament to how carefully the standard designed the idea of a Lambda expression and fit it into the existing framework we had for function objects.
So here's how it actually all works. And this is the slide we say is sort of like the takeaway. You write your Lambda expression. The compiler will generate the function object data type. Remember the function object data type? This is the class with all the boilerplate. And there's a lot of pieces the compiler will write, and it knows exactly how to do it. At runtime, the constructor of this function object data type is called. This is what produces a closure. And the closure, you can call it immediately, store it in a variable like we've been doing, putting it in myLam, or you can pass it to another function. As programmers, we normally write classes, methods. To us, as we were looking at Lambda expressions, everything feels sort of backwards. And it is, because you're writing the function class, you're actually writing that function call operator. You're not writing the class, but the insides. So our suggestion is, think of this as, yes, you are just writing that single function call operator, and you're going to let the compiler write everything around it, the class, and instantiate it.
So now that we've looked at the structure and the layout of a Lambda expression, we want to go over some examples. And the first one we're going to show uses a Lambda expression as a callback. So for a quick review, we want to look at the definition. From computer science, we get the idea that a callback is a function which is passed as an argument to another function. Now, callbacks can be passed as a function pointer or a function object in C++. So this is nice. We can write a Lambda expression and then pass the resulting closure. And our callback will be invoked at the discretion of the receiver based on what it's doing.
So here's an example, and we're showing a callback, and it's being passed to an algorithm. On the first line, we're just declaring a vector of integers. In example A, we define a free function, because that's the part we're going to show first. And this is my callback, and it's responsible for testing if the pass parameter is greater than 5. The algorithm COUNTIF, it expects a callback, and it will just return a bool when it's invoked, and this is just going to count how many times we got a true.
In example B, we're doing exactly the same thing, but using a Lambda expression. All the relevant code is located in place on this one line. And our belief is this is much more readable and convenient because you don't have to look somewhere else in the code to find out what my callback is testing for. You can just read it right here.
Keep in mind that both example A and example B, they will produce the same result. We are just saying that we think example B is easier to read. And again, you're not having to go search for where the callback was defined for example A. We do have a question. It's a little squished. Since the constructor of the function object is called, is there significant performance difference between a regular function? We didn't, do you know a timing study on that?
We haven't benchmarked that.
Yeah,
but
we haven't benchmarked.
If you have a function call and you turn it into an equivalent Lambda expression, then you won't have a capture clause because functions certainly can't capture.
Yeah.
So the constructor will be trivial. I'd be surprised if any good compiler will generate more expensive code for the Lambda expression case.
So here's an example taking off from the last one. And again, now we're doing a capture clause. So our Lambda expression is going to capture the value of CH from that local scope. And in this example, we're going to check if str starts with the character that we want to match on. The closure returns true or false, just as it did before, and COUNTIF will return the number of matches. Writing this callback as a free function doesn't work. There's no place to store the value for CH.
So here's a place where a Lambda expression allows us to do something which is impossible with a function pointer because there's nowhere to put the data, and messy with a function object. You would need to write a lot more boilerplate to do this if you wanted to do it manually.
Okay. Oh, you want to look at the question? Will example B on slide 36 prevent jump?
Assembly.
I have not looked at the assembly.
Yeah, it would that would be very compiler specific.
Yeah, compiler specific.
And the other question was, how can a Lambda recurse? And I believe the answer is it can't, because you can't name the Lambda within its own body.
Yes.
There's no way to refer to it.
There's no way to refer to it.
So now let's look at how you would capture something like an std unique pointer, which is not copyable. So we start this example by calling makeUnique to construct a new widget, which returns a unique pointer to the new widget object. We're then going to use a move capture to move the unique pointer into the closure. And notice this uses a generalized lambda capture, so this code requires C++14.
We want to mention that we could have done this capture and named the variable myPointer, just like it was in the outer scope, instead of calling it captured pointer. But we suggest you avoid this and use a different name. It reads a lot better in the code if you actually change the name in the generalized lambda. And since the lambda expression captures the unique pointer, the compiler is actually going to generate this class, and it's not going to be copyable.
And this makes sense because the unique pointer is actually stored in the closure. So this closure can't be copied. The side effect of this is you cannot store this closure in an std function object because std function requires that the object it stores be copyable.
Is there a performance benefit for using lambda versus a function call? Readability, that would definitely be one of the issues that I would look at. I am always looking to make my code more readable. So that feels like a performance benefit. In terms of a timing study, you would have to sort of look at the code. But again, remember, you're writing the function call operator. The compiler is doing all the outer work. And we strongly believe that this is a part where the compiler has really been able to optimize and write it more efficiently than I can.
Also, in general, in C++, calling a function pointer is more expensive than calling a function object in many cases. So lambda expressions get that benefit, that function pointers are actually not preferred. So we've mentioned that when you store a closure, you almost always use the data type auto. But how do you declare the data type if you're passing a closure to another function? Because you can't declare a function parameter with auto.
So we have 3 lines of code here, and we're declaring our lambda expression and assigning it the closure to myLam. And then you can see we're passing myLam to do thing A and do thing B. In example A, we're declaring a templated function, which has the ability to deduce the type, the data type of our closure. In example B, we're actually storing our closure in an std function. And this is 2 different ways to do it. They both work. And we did want to mention that the syntax for the declaration of std function, it is a little bit odd. First, we have the int that declares the return type, and the double, that is the data type for the parameter. So there's something kind of fun with std map, but not everybody uses it. You can actually use the third template parameter to redefine and say, how should the comparison happen? And what you need to do is specify a template parameter. So in this example, we're passing a function object data type, myCompare. We wrote the struct, we wrote the operator open close, and we're just passing this information. So the operator open close method, it's pretty darn simple, and it's doing a comparison. This is pretty much how a map works anyway. We're doing the less than comparison. And as you can see, myCompare, just the data type is passed. But this is sort of the old-fashioned way. We should be using a lambda expression.
So we're going to start by declaring a lambda expression which implements a comparison. And you'll notice the body is exactly the same as we had when we were using a function object. The code's a bit easier to read because we've removed a lot of extraneous boilerplate. But notice we have to use decal type myLam for the third template parameter because we need to specify a data type for the third parameter of std map. Now in this example, specifying the data type is sufficient because our map can default construct an instance of the closure. However, if you want to take advantage of the fact that lambda expressions can capture values, for example, you might want to capture a particular locale to do a locale-aware string comparison. Keep in mind, if you add a capture to the lambda expression, then you're going to need to pass an instance of the closure when you construct the map, because the closure type will no longer be default constructible.
So as a reminder, if any parameter uses the data type of auto, it's called a generic lambda. When you have a generic lambda, the compiler is actually going to generate a templated function call operator. So in this example, we have the word auto, one of them is in yellow and one of them is in purple. But these are not the same auto. They do different things.
The auto that we're showing in yellow is not what makes this expression a generic lambda. This auto is being used for type deduction of the closure, as you normally do with any lambda expression. The auto in purple is the function template argument, and this is what makes it a generic lambda. And it's important to be aware of this because the rules for auto type deduction of a variable are not quite the same as the rules for data type deduction in a function template argument. Now in C++20, when we gain the ability to use t as a template parameter, as a named template parameter, if you replace the purple auto with a t, you still call the expression a generic lambda.
And we did mention before, but it's worth bringing up, that once you add those template parameters and you're using 20, you can mix and match. So you could have an auto and a t. And again, as long as there's one auto or one t, then you have a generic lambda. So we always like to toss in one sort of surprising example. And this is our surprising example. Structured bindings. They're not technically variables, but there was an oversight and they don't work in a capture. Our code on line A, it declares two structured bindings, one name X and the other Y. Line B is a normal lambda expression with a capture clause. And in C++17, line B is actually ill-formed. However, MSVC and GCC said, that's fine, I don't care. I'm just going to go ahead, I'm not reporting an error. I know you wanted to do a capture and everything works fine.
However, this was incorrect because this shouldn't be allowed in C++17. This bug was resolved in the C++20 standard, and they allowed capturing a structured binding. Unfortunately, Clang has not caught up with C++20. So if you test this code on the very latest version of Clang, it still reports an error saying you cannot capture a structured binding. That's a known bug. The workaround for this is quite simple, but silly. You can use a generalized lambda capture, and instead of just capturing x, you capture x equals x, because a generalized capture of a structured binding works. So this will work in 17 or 20, no matter which compiler you use and how they're interpreting the standard.
So there's your silly workaround. Just use a generalized capture of x equals x, and you don't have to worry which compiler you're using. So we decided to close our talk with a nice summary, especially since, well, we kept confusing generalized capture and a generic lambda. So we thought this slide really represents everything we've talked about.
This talk had a ton of detail in it, and we hope everyone learned some definitions, the difference between a lambda expression and a closure, maybe a bit about how to do a move capture, or some information about how C++20 added a lot of new clauses.
We thank you for attending our talk. If you have questions, please post them. We will be around in the hallway track later. You can also reach us on Twitter or by email. And keep in mind, we do have a YouTube channel. We thought we would mention that. So as you can see, this is just a list of some of our other talks. We hope you subscribe to our channel and watch some of our videos. And again, if you're interested in the CopperSpice project, please come talk with us. And we're going to put up some contact information and answer some questions. Map filter. How would you, let's see. Can you read it? The Trinity, map, filter, reduce, fold. Do you have any examples of these with a Lambda?
Not in this talk.
Not in this talk, we don't. On our YouTube channel, we do have a few more examples of how to work with Lambda expressions, and most of those related to callbacks.
But that sounds like a great topic.
That sounds like
so
a great
maybe
topic.
we'll cover that
We'll
in a
cover
future
that.
video. And how would you wrap Lambdas using std function? Well, there's really not much wrapping involved in it because std function can store any function object. So you just assign the Lambda expression to some variable of the type std function with the appropriate signature, and it's implicitly converted. If that didn't answer your question, please post again.
Is there an equivalent wrapper? Sorry, it takes a moment to read these. Is there an equivalent wrapper to you that allows non-copyable closures? Not based on the definition. Go for it.
Yeah, that's kind of a regrettable oversight in the standard that they don't have a move-only function object container. And I actually saw something on Twitter a couple of weeks ago. Somebody was, I forget the name, was mentioning if your code base doesn't have a move-only function object wrapper, now is probably the day to write it. So yeah, no, there's nothing in the standard for that, but it's
not yet.
It's pretty common.
But they do take submissions. So do you use function templates? Well, I will say that we just rewrote a major section of CopperSpice that was released last week, rewriting how
probably reread the whole question.
Yeah, of how variants work, and we do make heavy use in CopperSpice of Lambda expressions.
But I would say the question of do you typically use function templates or std function parameters when we're in CopperSpice, and we would typically use function templates. The reason being that most of our code is quite template heavy to begin with, so it's very natural to do this. Really, the only reason to use std function is if you want the type erasure behavior and you're willing to lose the closure data type, and you're willing to pay a runtime cost for it because it does require a heap allocation to store the function object. So in general, if you can use a template, prefer that, and we usually can.
Are there any more questions? I see that our screen is blank and we have about 3 more minutes or so. Well, if that's it, then thank you so much for attending. We appreciate your being here. Ooh, there's another question. What are the most observed gotchas? To me, the most observed one is a capture where you've done a move capture, and then somebody tries to access that variable, not realizing that it's been captured and it's already been moved into the Lambda expression. One of the other things that we saw when we were, like I said, rewriting QVariant and the variant classes in CopperSpice, and we were using std visit, we were using some Lambda expressions that got a little bit lengthy, and they do use if const expr, and so the syntax, you have to watch how you break up the lines and format the code. And if we didn't format it well, it was hard to debug and hard to read. So that made it easier. Actually, formatting it well made it easier for our code review.
Another really interesting behavior that I've noticed is very few people use Lambda expressions with the mutable keyword. So normally when you capture something, it's constant and it doesn't change throughout the lifetime of the closure. If you start using Lambdas that have mutable data in them, you will discover places in the code base where you are copying closures. And this means you're getting a copy of all the state in the closure. And this can be really surprising sometimes because you invoke it one time and you modify the data, and then it gets invoked another time in a different piece of code, and the data is back to what it had been. So watch for that carefully. That's another reason to use a move-only function object container.
I'm not sure how long they talked about it. That's an interesting history question. I believe Lambda expressions, well, they were added in 11, and I'm not sure how long the proposals existed, but based on other things that have been added to the standard, I would suspect it was quite a few years. If somebody else has some information from the standards committee of when the initial proposal started. That's something we could probably look up and post that in the chat later on.
Mm-hmm. And it is clear that however long they spent standardizing Lambda expressions before 11, it wasn't quite long enough, because it meant that in C++ 11, Lambdas were basically unusable with move-only types, and you didn't really get that until generalized capture in 14. So I would view Lambda expressions in C++ 11 as sort of being a beta release.
Yes, there were a lot of things changed in 14 and in 17, especially like with capturing this.
So they're clearly still under active development.
Yes. So I think our time is up. Thank you, everyone, for attending. We appreciate it. If you have other questions, we're going to be on the hallway track, and that completes our presentation.
Thank you.
Thank you.